Caesar the Circulate talking to you about trigonometry and the unit circle. Trigonometry? Sounds like monkey business to me.
First vocabulary term is the unit circle. That would be a circle with a radius of 1 unit and its center at the origin. So down here we have a pretty simplistic sketch of the unit circle where we have a circle with the center at the origin and a radius of 1 unit. Now we are going to dive into the unit circle way more in depth later on in this lesson, but for right now all you need to know is that it's a circle with the center at the origin and a radius of 1 unit. Second vocabulary term is a reference angle. That would be the smallest angle between 0 degrees and 90 degrees that you can form with the terminal side of an angle and the x-axis. So down here we have 4 different examples, and these examples are just going to show you how to create a reference angle based on which quadrant your terminal side ends up in. If your terminal side of your angle is in quadrant 1, then your reference angle is just going to be this angle right here, which would be 60 degrees. Remember, it's the angle formed with the terminal side of your angle and the x-axis. If the terminal side of your angle ends up in quadrant 2, then again, to create the reference angle, it's just going to be the angle formed by the terminal side of your angle and the x-axis. That would be this 45-degree angle right here. If your terminal side of your angle ends up in quadrant 3, then your reference angle would be this angle right here. It's the angle formed by the terminal side of your angle and the x-axis, this 20-degree angle right here. And then, if the terminal side of your angle ends up in quadrant 4, again, the angle formed by the terminal side of your angle and the x-axis would be considered your reference angle. That would be this 80-degree angle right here. So if you recall, in our last lesson, we filled out the degree measures here and the x and y coordinates of each of the points at those specific degree measures on our unit circle. Today, we're going to actually show you what the unit circle is used for. And it's actually used to help us find the sine, cosine, and tangent ratios of angle measures that are multiples of 30 degrees and 45 degrees. And we can do this without even using a calculator. It's pretty cool. So let me show you how this works. First, let's quickly review each of the trig ratios. This is the sine ratio. And the sine ratio says, in a right triangle, the sine of an angle A is given by the following equation. Sine of angle A is equal to the length of the leg opposite angle A over the length of the hypotenuse, or shortened, sine of A is equal to opposite over hypotenuse. Now, the first thing to note is that the sine ratio, just like all the other ratios we're going to be dealing with today, require a right triangle. Next, let's look at this in terms of our example down here, right triangle ABC. So angle A right here, if we want to determine the sine ratio for angle A, it's going to be equal to the length of the leg opposite angle A. So which leg is opposite angle A? That would be segment BC over here. So we're going to have the measure of segment BC over the length of the hypotenuse. Remember, the hypotenuse is the side that's always opposite the 90-degree angle. So in this case, that would be segment AC. So the sine ratio for angle A in this example down here would be the length of the leg opposite angle A, which would be the measure of segment BC, over the length of the hypotenuse, which would be segment AC, the side that's opposite our 90-degree angle. That's how you create your sine ratio, opposite over hypotenuse. Now, the cosine ratio says in a right triangle, the cosine of an angle A is given by the following equation. Cosine of angle A is equal to the length of the leg adjacent to angle A over the length of the hypotenuse, or shortened, cosine of A is equal to adjacent over hypotenuse. So again, important to note that the cosine ratio, just like the sine ratio and eventually the tangent ratio, have to be right triangles. We're dealing with right triangles today. Next, when we're talking about the cosine of an angle, it's equal to the length of the leg adjacent to that angle over the length of the hypotenuse. So if we're looking at our example right here, right triangle ABC, coming from angle A, the cosine of angle A is equal to the length of the leg adjacent to angle A. Remember, the legs would be the short sides of your right triangle. So in this case, the length of the leg adjacent to angle A would be the measure of segment AB, over the length of the hypotenuse, the side opposite our 90-degree angle. So that would be the measure of segment AC over here. That's how you create your cosine ratio, adjacent over hypotenuse. Now, the tangent ratio says in a right triangle, the tangent of an angle A is given by the following equation. The tangent of angle A is equal to the length of the leg opposite angle A over the length of the leg adjacent to angle A. Or shortened, the tangent of angle A is equal to opposite over adjacent. So again, important to note, the tangent ratio, just like the sine and cosine ratios, we're talking about right triangles here. Next, it's important to see that in the tangent ratio, we're just dealing with the legs of our right triangle. We're not using the length of the hypotenuse for once. So if we're looking at our example down here, right triangle ABC, to create the tangent ratio for angle A, it's going to be equal to the length of the leg opposite angle A, which would be the measure of segment BC over here, over the length of the leg adjacent to angle A, which would be the measure of segment AB over here. That's how you create your tangent ratio, opposite over adjacent.
Fun fact, sometimes monkeys throw their own poop. Example time.
Now example 1 says find the exact value of sine of 240 degrees. So because 240 degrees is a multiple of 30 degrees, we can actually use the unit circle in order to find the exact value of the sine of 240 degrees. So the first thing we're going to do is draw a 240 degree angle in standard position. So we're going to draw our initial side as a ray on the positive x-axis. Then we're going to take our terminal side and rotate it 240 degrees counterclockwise. And at 240 degrees, we can put our terminal side. Now, in order to evaluate sine of 240 degrees, we need to use right triangle trig, meaning we need a right triangle. So how do we form a right triangle here? Well, what we're going to do is we're going to go to the point on the unit circle at 240 degrees, and we're going to drop an altitude that is perpendicular to our x-axis, thereby creating a little right triangle here. Now, do we know any of the angle measures in this little right triangle that we're going to form? Yeah, this angle right here is going to be the reference angle of 240 degrees. So how many degrees are between 180 degrees and 240 degrees? That would be 60 degrees. So we have a 60-degree reference angle that is going to be one of the acute angles in our right triangle. Now, if one of the acute angles is 60 degrees, that means the other acute angle is going to be 30 degrees. So we have now created a 30, 60, 90-degree right triangle. And we can use that in order to help us find some of these sides here. So how do we find the missing side lengths of this right triangle? Well, again, this is the unit circle, meaning that the radius of this circle is 1 unit in length. And if you look carefully at this right triangle that we've created, our hypotenuse, the side opposite the 90-degree angle, is a radius of the unit circle, meaning it would be 1 unit in length. So now we can use that in order to help us find the other two missing sides. So remember, in a 30, 60, 90-degree triangle, the short leg, the side opposite the 30-degree angle, if we multiply that by 2, we get the hypotenuse. Meaning if we have the hypotenuse, we can divide that by 2 to give us the short leg. Now the only issue is that this is on the coordinate plane, meaning that this side length of our triangle is on the negative x-axis, meaning that instead of being 1/2 unit in length, we're going to label it as negative 1/2 unit in length. Next, let's find the length of the longer leg, the side opposite the 60-degree angle. So remember, the shorter leg times rad 3 is going to give you the length of the longer leg. So 1/2 times rad 3 gives you rad 3 over 2. And again, this side length right here corresponds with the negative y-axis, meaning this side length right here we're going to label as negative rad 3 over 2. That's why this point right here on the unit circle is at negative 1/2 comma negative rad 3 over 2. Now that we have successfully labeled this triangle right here, we can go about evaluating the sine of 240 degrees. Remember, the sine ratio of a specific angle is just going to be equal to opposite over hypotenuse. And in this case, we're going to come from our reference angle. So our reference angle here is 60 degrees. What is the side length opposite that? That would be negative rad 3 over 2. And what would be the hypotenuse of this right triangle? Remember, that's always the side length opposite our 90-degree angle. That would be 1. So if we put negative rad 3 over 2 over 1 and simplify that, well, this over 1 is just this. So we get negative rad 3 over 2, meaning the sine of 240 degrees is negative rad 3 over 2, and you're done. Now, one thing I want you to note before we move on is that negative rad 3 over 2 also happens to be the y-coordinate associated with this point at 240 degrees on our unit circle. Interesting. Let's see if that holds up.
Why don't monkeys play cards in the jungle? There's too many cheetahs! You try! Ho!
Okay, doing the same thing. So we want to find the sine of negative 45 degrees. And because negative 45 degrees is a multiple of 45 degrees, obviously, we can use the unit circle to help us find that exact value. So the first thing we're going to do is draw our negative 45 degree angle in standard position, meaning we're going to draw a ray, our initial side, on the positive x-axis. Now our terminal side, we're going to rotate clockwise this time because it's a negative 45 degree angle. So instead of rotating counterclockwise like we do for positive angles, we're going to rotate clockwise. And we rotate clockwise 45 degrees until we end up with our terminal side right here. And again, we want to find the exact value of sine of negative 45 degrees. So to evaluate this trig function, we need to use right triangle trig, meaning we obviously need to create a right triangle. So from this point on the unit circle at 315 degrees, we're going to drop an altitude that is perpendicular to the x-axis. Now, do we know any of the angle measures in that right triangle that we're about to create? Well, yeah, this reference angle right here is 45 degrees. So if we were to create this right triangle, this would be a 45, 45, 90 degree triangle. meaning we can use the 45, 45, 90-degree triangle theorem in order to help us find the missing side lengths. So do we know any of these side lengths right now? Well, yeah, remember, this is the unit circle, meaning that the radius of this circle is 1 unit in length. And if you look carefully, the hypotenuse of this 45, 45, 90-degree triangle is a radius of the unit circle, meaning it is 1 unit in length. Now also recall, the 45, 45, 90-degree triangle theorem says in a 45, 45, 90-degree triangle, the legs are congruent and the hypotenuse, the side opposite the 90-degree angle, is equal to rad 2 times the length of a leg. So if I'm given the hypotenuse, then to get the length of the leg, I would obviously have to divide this by rad 2. So it would be 1 divided by rad 2. But we can't leave a radical in the denominator, so we multiply that by rad 2 over rad 2, and we end up getting rad 2 over rad 4, which is rad 2 over 2. So that would be the length of each of our legs. Now, because this is on the positive x-axis, we can label this as positive rad 2 over 2. But because this leg of our triangle dips into the negative y-axis, we would have to label this as negative rad 2 over 2. That's why this point on the unit circle right here is at positive rad 2 over 2, comma, negative rad 2 over 2. Now that we have successfully labeled all the sides of this right triangle, we can evaluate the sine of negative 45 degrees. Because remember, sine is just equal to the length of the leg opposite our given angle over the length of the hypotenuse. Now, which angle are we coming from? Well, we're coming from our reference angle in here, which would be 45 degrees. So from this angle, the length of the leg opposite our given angle is going to be negative rad 2 over 2, so that's going to go in our numerator. And the hypotenuse, the side opposite our 90-degree angle, is going to be 1, so that's going to go in our denominator. Now, what is negative rad 2 over 2 over 1? Well, this over 1 is just this. So we get sine of negative 45 degrees is negative rad 2 over 2. Now, what I want you to do is check that cheat code we were talking about last time. Remember, the sine of 240 degrees was just the y-coordinate of this point. Well, what is the sine of negative 45 degrees? Well, if you go to the point at negative 45 degrees, what's the y-coordinate? It's negative rad 2 over 2. That's exactly what we got. So it looks like we may have discovered a cheat code. Let's explore this a little more. Now example 2 says find the exact value of cosine of 45 degrees. Now because 45 degrees is a multiple of 45 degrees, obviously, we can use the unit circle in order to help us find the exact value. So how do we do this? Well, again, we're going to start by creating our angle in standard position. We're going to draw our initial side as a ray on the positive x-axis. We're then going to rotate our terminal side counterclockwise positive 45 degrees. Now we need to evaluate cosine of 45 degrees. In order to evaluate cosine, we need to use right triangle trig, meaning we need a right triangle. So how do we form a right triangle here? Well, we're going to go to our point at 45 degrees on the unit circle, and we're going to drop an altitude that is perpendicular to the x-axis. Now, when we do that, we create a right triangle in here. And in that right triangle, do we know any of the angle measures? Well, yeah, this angle right here, we already know is 45 degrees, meaning we have created a 45, 45, 90-degree triangle, and we're going to use that to help us find the missing side lengths here. So, in this triangle, do we know any of these sides? Yes, we have created this triangle on a unit circle where the radius of our circle is 1 unit in length. And in this triangle, our hypotenuse is a radius of this circle, meaning our hypotenuse would also be 1 unit in length. And because we know this is a 45, 45, 90-degree triangle, we can use the 45, 45, 90-degree triangle theorem, which says the lengths of the legs of this triangle are congruent, and the length of the hypotenuse is equal to rad 2 times the length of a leg. But if we're given the hypotenuse, and we want to go the other way, we have to divide this by rad 2. And we've already seen that that's going to give us rad 2 over 2. Now the question is, are these legs going to be positive rad 2 over 2 or negative rad 2 over 2? Well, this side length right here is located on the positive x-axis, so it would be positive rad 2 over 2. This leg right here is located in the positive region of the y-axis, so it would also be positive rad 2 over 2. That's why this point on the unit circle is at positive rad 2 over 2, comma, positive rad 2 over 2. Now that we found all the missing side lengths in this triangle, we can evaluate cosine of 45 degrees, because remember, cosine is just adjacent over hypotenuse. And in this case, we are coming from this angle, our reference angle, this 45-degree angle right here. Now, we want to find the length of the leg adjacent to 45 degrees. So the length of the leg adjacent to 45 degrees would be this positive rad 2 over 2 here. Remember, our hypotenuse is technically adjacent to this angle as well, but we're talking about the length of the leg adjacent to 45 degrees. We also need to find the hypotenuse to put that in the denominator. Remember, that's the side opposite our 90-degree angle. That would be this 1. So we end up getting rad 2 over 2 over 1, which simplifies to rad 2 over 2. So we have found that cosine of 45 degrees is equal to rad 2 over 2. Now, is there any cheat code that we could possibly associate with this? Well, if we look at our point here, positive rad 2 over 2, that's both the x and the y coordinate. But we found that sine of our given angle was equal to the y coordinate. So maybe cosine of our angle is equal to the x coordinate. Let's test this out.
What did the monkey bring to the party? Chips and dip! Oh, you try!
Okay, doing the same thing. We want to find the exact value of cosine of 210 degrees this time. And because 210 degrees is a multiple of 30 degrees, we can use the unit circle to help us figure this out. So the first thing we're going to do is create our angle in standard position. So we're going to draw our initial side as a ray on the positive x-axis, and then rotate our terminal side counterclockwise positive 210 degrees. We then recognize that we're about to evaluate cosine of 210 degrees, meaning we need to use right triangle trig, meaning we need a right triangle. So from this point at 210 degrees on the unit circle, we're going to drop an altitude that is perpendicular to the x-axis. Now, do we know any of the angles in that right triangle? Well, yeah, we know this reference angle right here is just going to be the difference between 210 degrees and 180 degrees, which is 30 degrees. So it looks like we have created, again, a 30, 60, 90 degree triangle, and we can use the 30, 60, 90 degree right triangle theorem in order to help us find the missing side lengths here. First, let's label one of the sides that we know. We know that because this is a unit circle, that the radius is 1 unit in length, and the hypotenuse of this 30, 60, 90 degree triangle is a radius of our unit circle. Therefore, it also must be 1 unit in length. Now, if you recall, the 30, 60, 90 degree triangle theorem says everything is based on the short leg, the side opposite the 30 degree angle. If I multiply that by 2, I get the hypotenuse, meaning if I have the hypotenuse, I can divide that by 2 to give me the length of our shorter leg. Now, the only issue is the shorter leg's not just going to be 1/2. Because this side length is in the negative portion of the y-axis, we have to label this as negative 1/2. Next, we can find the length of our longer leg, the side opposite our 60 degree angle. And remember, that's just going to be rad 3 times the length of our shorter leg. And because this side length lies on the negative portion of the x-axis, it is also going to be negative. That's why this point on the unit circle is at negative rad 2 over 2, comma, negative 1/2. So now that we have found the missing side lengths of this 30, 60, 90 degree triangle, we can evaluate cosine of 210 degrees because cosine, remember, is just equal to adjacent over hypotenuse. So which angle are we coming from? Well, we're coming from our reference angle right here, this 30 degree angle right here. So the length of the leg adjacent to this reference angle would be this leg right here. That would be negative rad 3 over 2. That's going to go in our numerator. And the hypotenuse is the side length opposite our 90 degree angle. That would be this 1 right here. That's going to go in our denominator. And negative rad 3 over 2 over 1 just simplifies to negative rad 3 over 2, meaning cosine of 210 degrees is equal to negative rad 3 over 2. Now let's quickly check to see if our cheat code held up. Remember, we found that the y-coordinates of these points on the unit circle correspond to the sine of the given angle. And we're thinking that the x-coordinates of these given points on the unit circle correspond to the cosine of your given angle. And it looks like cosine of 210 degrees, yes, that would be the x-coordinate of this point on the unit circle. So it looks like we found a cheat code. We'll get into that more later on. Now, example 3 says find the exact value of tangent of 135 degrees. So again, 135 degrees, that is a multiple of 45 degrees, so we can use the unit circle to help us evaluate this. So we're going to begin by drawing our angle in standard position. We draw our initial side as a ray on the positive x-axis and rotate our terminal side positive 135 degrees counterclockwise. Now that we have our angle, we can start evaluating tangent of 135 degrees. And remember, tangent, that's a trig function, meaning we need to use right triangle trig, meaning we need a right triangle. So let's form a right triangle by dropping an altitude from this point at 135 degrees that is perpendicular to our x-axis. Now when we do that, are we going to know any of the angles in this triangle? Well, yeah, we know the reference angle right here is just going to be 180 minus 35, which is 45 degrees. So we again have a 45, 45, 90 degree triangle, and we can use the 45, 45, 90 degree triangle theorem in order to help us find the missing side lengths here. Well, don't we already know a side length? Yes, this is a unit circle, meaning it has a radius of 1 unit, and because the hypotenuse of this 45, 45, 90 degree triangle is a radius of the unit circle, it also has a length of 1 unit. Now, we can use the 45, 45, 90 degree triangle theorem to help us find the other 2 missing side lengths. Remember, in a 45, 45, 90 degree triangle, the legs are congruent and the hypotenuse is equal to rad 2 times the length of one of the legs. So if we're given the hypotenuse, to find the legs, we just divide the hypotenuse by rad 2. Now, we have found that each of these are then going to be rad 2 over 2. The only issue is, are they positive or negative? Well, this side length of our triangle is on the negative portion of the x-axis, meaning it is going to be negative rad 2 over 2. This side length right here is in the positive portion of the y-axis, meaning it is going to be positive rad 2 over 2. That's why this point on the unit circle is at negative rad 2 over 2, comma, rad 2 over 2. Now that we have found the missing side lengths of this right triangle, we can evaluate tangent of 135 degrees because remember, tangent of an angle is just equal to opposite over adjacent. So which angle are we coming from? Well, we're coming from this reference angle right here, this 45 degree angle. So the length of the leg opposite our given reference angle would be rad 2 over 2. That's going to go in our numerator. The length of the leg adjacent to our given reference angle would be negative rad 2 over 2. That's going to go in our denominator. Now what is positive rad 2 over 2 divided by negative rad 2 over 2? Well, that's just going to be negative 1, meaning tangent of 135 335 degrees is equal to negative 1. Now you think to yourself, we found a shortcut for sine, we found a shortcut for cosine, there has to be a shortcut for tangent as well. Well, if you recall, tangent is just equal to sine over cosine. So if we know that sine of a given angle is going to be the y-coordinate of that point on the unit circle, and cosine of that same angle is going to be the x-coordinate of the point on your given unit circle, then wouldn't tangent just be the y-coordinate over the x-coordinate, which is exactly what we just found here? Oh, interesting. Let's see if that holds up.
What did the monkey wear when he cooked? An apron! Oh, you try.
Okay, doing the same thing, except this time we're finding the exact value of tangent of 330 degrees. And because this is a multiple of 30 degrees, we can use the unit circle to help us evaluate this. We're going to start by sketching a 330 degree angle in standard position. We start with our initial side as a ray on the positive x-axis, and then we swing our terminal side counterclockwise positive 330 degrees. Now that we've created our angle, we can go about evaluating tangent of 330 degrees. And remember, tangent is a trig ratio. And in order to use right triangle trig, we need a right triangle. So we're going to create a right triangle by dropping an altitude from our point on the unit circle at 330 degrees so that it's perpendicular to the x-axis here. Now, in that right triangle we're about to create, do we know any of the angle measures? Yes, we know that the reference angle right here is just the difference between 360 degrees and 330 degrees, which is 30 degrees, meaning we again have created a 30-69 degree triangle. So we can use the 30-69 degree triangle to help us find the missing side lengths here. Well, do we know any of the side lengths? Yes, we know that because this is a unit circle, it has a radius of 1 unit, meaning that because the hypotenuse of our triangle right here is a radius of the unit circle, it also has a length of 1 unit. Now that we know this side length, we can use the 30-69 degree triangle theorem in order to help us find the other missing side lengths. Remember, in a 30-69 degree triangle, everything is based on the short leg, the side opposite the 30 degree angle. The short leg times 2 is going to give you the length of the hypotenuse, meaning if you have the hypotenuse and you want the short leg, you just divide that by 2 and you end up getting that this side length right here would be 1/2. But before you write 1/2, this side length is in the negative portion of the y-axis, meaning this side length we're going to write as negative 1/2. Next, let's find the length of the longer leg in this 30-69 degree triangle. Remember, the length of the longer leg is just rad 3 times the length of our shorter leg. But before you write negative rad 3 over 2, this side length is on the positive portion of the x-axis, meaning its side length is actually going to be positive rad 3 over 2. That's why this point on the unit circle is at positive rad 3 over 2, comma, negative 1/2. Now that we've found the missing side lengths, we can actually go about evaluating tangent of 330 degrees. Because remember, tangent of an angle is just equal to opposite over adjacent, meaning we need to find the length of the leg opposite our given angle and put it over the length of the leg adjacent to our given angle. So which angle are we coming from? Well, we're coming from our reference angle in here, this 30 degree angle. The length of the leg opposite our given reference angle would be this side length over here, negative 1/2. That's going to go in our numerator. The length of the leg adjacent to our given angle is going to be this side length over here, positive rad 3 over 2. That's going to go in our denominator. Now we simplify negative 1/2 over rad 3 over 2. That's the same thing as negative 1/2 divided by rad 3 over 2, which is the same thing as negative 1/2 times the reciprocal of rad 3 over 2, which is 2 over rad 3. We then multiply the numerators and denominators together, and we can't leave a radical in the denominator, so we multiply the numerator and denominator by rad 3, and we end up getting negative rad 3 over rad 9, which is negative rad 3 over 3. So we have found that the tangent of 330 degrees is negative rad 3 over 3. Now let's check our cheat code, make sure that checked out. Remember, the cheat code for tangent is just the y-coordinate over the x-coordinate because it's sine over cosine. So the point located on the unit circle at 330 degrees, the y-coordinate over the x-coordinate, is that what we get? Yes, that's exactly what we just did. So that would be the cheat code for tangent. Now, the cheat codes, let's make it official. When finding the sine, cosine, or tangent of an angle in the unit circle, the sine of a given angle is equal to the y-coordinate, the cosine of that angle is equal to the x-coordinate, and the tangent of that angle is equal to the y-coordinate over the x-coordinate. So let's use our cheat codes a little bit to show you how much easier it is than creating a right triangle every time. Example 4 says find the exact value of the given trig function. So this time we're trying to find the sine of 180 degrees. So rather than create a right triangle, we just go to 180 degrees on the unit circle. And remember, sine of that angle is just equal to the y-coordinate of that point on the unit circle, which is going to be 0 in this case. So sine of 180 degrees is 0, and you're done. Look how easy that is. Part B, cosine of 45 degrees. We go to 45 degrees on the unit circle. Remember, cosine is just the x-coordinate of your given point on the unit circle, which is rad 2 over 2, meaning cosine of 45 degrees is just rad 2 over 2. Wow, that's so much easier. Next, we want to evaluate sine of negative 30 degrees. So where is negative 30 degrees on the unit circle? Well, you start at 0 degrees, and this time, instead of rotating counterclockwise, we're going to rotate clockwise 30 degrees. So sine of negative 30 degrees is the exact same as sine of positive 330 degrees. Those are coterminal angles. So in order to evaluate this, all we have to do is just take the y-coordinate of that point on the unit circle. So what is the y-coordinate? That would be negative 1/2, meaning sine of negative 30 degrees is the exact same as sine of 330 degrees, which is equal to negative 1/2. Part D, we want to find tangent of 120 degrees. So where is 120 degrees on the unit circle? Here it is. And remember, tangent requires that you take the y-coordinate of your point on the unit circle and put it over the x-coordinate of your point on the unit circle. And then you just have to simplify that fraction. So rad 3 over 2 divided by negative 1/2 is the same as rad 3 over 2 times the reciprocal of negative 1/2. So then we multiply the numerators and denominators, and the 2's actually cancel each other out, and we're just left with negative rad 3. So tangent of 120 degrees is equal to negative rad 3. And you're done.
What do you call an angry monkey? Furious, George! Oh, you tried.
Okay, first we want to evaluate cosine of 180 degrees. So we find 180 degrees on the unit circle. Remember, cosine is just equal to the x-coordinate of your given point. So what is the x-coordinate here? That would be negative 1, meaning cosine of 180 degrees is equal to negative 1. Sine of 210 degrees. To evaluate that, we locate 210 degrees on the unit circle. Here it is. And remember, sine of a given angle is just equal to the y-coordinate of that point on the unit circle, which in this case would be negative 1/2. So sine of 210 degrees is just equal to negative 1/2. Cosine of negative 210 degrees. Well, how do we find negative 210 degrees on the unit circle? Well, remember, instead of rotating counterclockwise like we do with positive angles, we need to rotate clockwise like we do with negative angles. So to rotate negative 210 degrees, we rotate negative 180 and then negative 30 degrees more. So cosine of negative 210 degrees is the exact same as cosine of positive 150 degrees. Those are coterminal angles. We then remember that cosine of a given angle in the unit circle, we just take the x-coordinate of that point, which in this case would be negative rad 3 over 2. So cosine of negative 210 degrees is the exact same as cosine of 150 degrees, which is equal to negative rad 3 over 2. Last but not least, we have tangent of 90 degrees. So tangent of 90 degrees, we go to 90 degrees on the unit circle. And tangent, remember, is equal to the y-coordinate over the x-coordinate. So in this case, that would be 1 over 0. Now, 1 over 0. Oh, we can't divide by 0. So anytime 0 is in the denominator, remember, you just write undefined. And that's your answer.